All right. Now we're going back to page 31, and we're going to compute limits involving absolute values. So the first remark here is that absolute values are actually going to be considered as piecewise defined functions. What I mean by this is that if you are computing the absolute value of an expression, if the expression is positive, like for example, if you're computing the absolute value of 5, you're not doing anything to it. If the expression is negative, like for example, if you're computing the absolute value of -5, then you're going to multiply the inside by -1 to make it +5. So maybe just to illustrate that, I'm just going to do an example here with numbers. For example, if you do the absolute value of -5, we know it's 5, but another way to do this is to say, well, let's multiply the inside by -1, and then you're going to get 5 again. So in other words, we are changing equations for the absolute value of the expression whenever the expression is equal to 0. So at 0, you could use a or minus a. Bigger than 0, you're going to use a. Smaller than 0, you're going to use -1 times a. So absolute values are going to be considered as piecewise defined functions. So the first thing that, not the first thing, but if you have a problem with an absolute value and if there is something bad with it, the first thing you need to do is that if you have absolute values of zeros, you need to get rid of them, okay, and treat them as piecewise defined function. So for example, we have to compute the limit as x approaches 1 of x squared minus 1 over the absolute value of x minus 1. So if we try it first, so if we plug 1 inside, so you get 1 squared minus 1 over 1 minus 1, you're going to get what? Big surprise again here. Okay, 0 over 0. And we know 0 over 0 are super bad cases. Okay, so that's pretty bad stuff. But what we have to notice here is that we have the absolute value of something, and that something is 0. So we have a change of equation here around 1 for x minus 1 inside the absolute value. So we need to go left and right. So let's go left first. So limit as x approaches 1 minus, so we have x squared minus x over the absolute value of x minus 1. And might as well write it down too. We're going to compute or define first and then compute the right limit as x approaches 1 plus of x squared minus 1 over the absolute value of x minus 1. So after that, the left and right limits are defined, we need to get rid of these absolute values. For the first one, if you look at the inside, so if you pick a number slightly smaller than 1, for example, 0.9, if you go 0.9 minus 1, you're going to get minus 0.1. So you can notice here that the inside is actually negative. And because it's negative, if you want to get rid of the absolute value, you need to multiply the inside by minus 1. So this limit is the same as the limit as x approaches 1 minus of x squared minus x squared minus 1, sorry, over down there here we have minus 1 times x minus 1. Sorry, x minus 1. So this is how we get rid of that absolute value. So this absolute value becomes minus 1 times x minus 1, making sure that it's now positive for any input strictly less than 1. So, and this is actually first application of the holy old principle, getting rid of the absolute value. Minus 1 times x minus 1 is not the absolute value, but it is on the left side, so the limits are going to be the same. Sadly, if you plug 1 in here, you're still going to get a 0 over 0 case, but now we have a rational expression, so we no longer have any square roots. We have a rational expression, so might as well just factor the polynomial at the numerator. So we have a difference of square here, so we're going to get the limit as x approaches 1 minus of x minus 1 times x plus 1, all that over minus 1 times x minus 1. And now you can see it. Okay, so the two x minus 1, they cancel perfectly, leaving behind x plus 1 over minus 1. And now, so this is now a brand new limit to compute. So the limit as x approaches 1 minus of x plus 1 over minus 1. You could write minus 1 or minus x plus minus 1. That would work too. Does not really matter here. And now if you plug 1, so be careful. So actually here, the cancellation is another application of the Holy-Old principle. So there's a lot of them here. And now if you plug 1, not 1 minus, remember, this is a common trap here. 1 minus or 1 plus, you plug those symbols, okay, if you have a root of 0 problem or a division by 0, like a non-zero number divided by 0, or eventually ln of 0. But here there's no such problem. Okay, we've simplified our expression and we try it. Now we replace x by 1. Okay, the limit notation is gone. You get 1 plus 1 divided by minus 1, and that simplifies to minus 2. So the left limit of x squared minus 1 over the absolute value of x minus 1 is minus 2. Now let's do the right-sided limit. So for the right-sided limit, it's very, very similar. So now we see that the inside, so if you look at the inside of your limit at the denominator, if you pick a number slightly bigger than 1, like 1.1 minus 1, it's going to be positive. And how do you get rid of an absolute value? When the inside is positive, well, you just erase. Okay, so the absolute value. So here we go. Boom. Okay, so you get the exact same expression. Okay, but now it's a right limit, and you at the denominator, instead of having at the denominator, you only have x minus 1. But of course, if you plug 1, you still have a 0 over 0 problem. So before moving on, just to be consistent here, this is an application of the Holy-Old principle. So if you factor the exact same way, so you're going to get the limit as x approaches 1 plus of x minus 1 times x plus 1. So it's the same factorization. Normally left and right, everything is the same. It's just the sign of the absolute value that changes. So now you can see that the x minus 1 again simplifies, reducing this expression to the limit as x approaches 1 plus of x plus 1. Now you're plugging 1, not 1 plus, just 1. And you're going to get 1 plus 1. And then you're going to get 2. So the right limit here, the limit as x approaches as x approaches 1 plus of x squared minus 1 over the absolute value of x minus 1 is now plus 2. And then, of course, if you compare these two limits, they're not equal. So these two limits are not equal. So when you compare them, so they're not equal. I'll just write this in red. So they're not equal, the left and right. So therefore, okay, the limit as x approaches 1 of x squared minus 1 over the absolute value of x minus 1 does not exist. All right, next example now. All right, next example, we have to compute the limit as x approaches 2 of 1 over x minus 2 plus 1 over the absolute value of x minus 2. So the first thing, you just plug 2, hope for the best, okay, but brace for the worst. Okay, so here, 2 minus 2, 1 over 2 minus 2, minus 1 over absolute value of 2 minus 2. What happens now? We have 1 over 0. That's already bad. Okay, so by itself, minus 1 over the absolute value of 0. So a lot of bad things going on here. So we have the absolute value of 0 when x is 2, and we have a bad, okay, we have a bad division by 0. So, but both are treated the exact same way. You need to go left and right. Okay, so that's bad. And to some extent, so that's bad, and to some extent, that's also bad, the absolute value of 0. You need to go left and right for both. So first, let's define these left and right limits. So let's compute the limit as x approaches to minus of 1 over x minus 2 plus, oh, that was, sorry, I said minus earlier, was a plus here, plus, just a bunch of pluses, plus 1 over the absolute value of x minus 2. So first thing, always get rid of your absolute value. So when x is smaller than 2, the inside here will be negative. 1.9 minus 2, that's going to be negative. So to get rid of the absolute value, you need to multiply the inside by minus 1. So this limit will become, that's a whole principle application. This limit will become the limit as x approaches to minus of 1 over x minus 2 plus 1 over minus 1 times x minus 2. Now you can simplify this a bit. So the minus 1, I'm just going to put it up front. So this is the same thing as the limit as x approaches to minus of 1 over x minus 2 minus 1 over x minus 2. And here, beautiful thing, we have the same term twice being subtracted. So these two are going to simplify down to nothing. So you're going to be computing the limit as x approaches to minus of 0, and you're just going to get 0. So the left limit is simply 0 in that case. Now let's define and compute the right limit. So the limit as x approaches to plus of 1 over x minus 2 plus 1 over the absolute value of x minus 2. So now for that one, the inside here, so if you pick a number slightly bigger, will be positive. So you're going to be dealing with, to deal with the absolute value, you just need to erase it. So when it's positive, you do nothing to it, you just erase it. So you get the limit as x goes to 2 plus of 1 over x minus 2 plus 1 over x minus 2. And now these two things are adding up. So a potato plus a potato is 2 potato. So by the way, this is an application of the whole principle here. So you get the limit as x approaches to plus of 1 over, sorry, not 1, but 2 now. So 2 over x minus 2. And sadly, if you plug 2 in there, you're going to get a division by 0. So I'm just going to write this up. So I know, okay, if I plug 2 inside, I'm going to get 2 over 0. So that's my green light. If you have a division by 0, you have to replace x by 2 plus. So you get 2 over 2 plus minus 2, and 2 plus minus 2, that's 0 plus, and 2 over 0 plus, that's plus infinity. So of course, when you compare the two limits, these two limits are not equal. And because they're not equal, therefore, the limit as x approaches, oh, let me just go back here. Need some room. So the limit as x approaches 2 of 1 over x minus 2 plus 1 over absolute value of x minus 2 does not exist. Away, it does not exist. All right, that's it for absolute values. And actually, that's it for that section. Okay, bye-bye.